So today, I'm going to talk about what the title talks about. So my perspective is maybe a little different than a Poisson geometry conference, although the word Lie algebroid and Lie groupoid is in the title, so I feel justified. At one point, I will use the word Poisson, so again, I feel justified. But yeah, so my perspective is I was kind of inspired by this construction of Alain Kahn of his tangent groupoid, and then later by the work of Eric Van Erp and Robert Youngkin and Choi Ponge, to define a new groupoid called this oscillating tangent groupoid, which they used Van Erp and Youngkin to define like a new sort of pseudo differential calculi. And right around the time I came to Toronto to do my PhD, Eckhard and his past student Yanis Lazaides were developing this theory of weightings. And so I kind of wanted to understand how they're the same thing and, how these can be useful for the calculus and index theory thing. Okay, so just like a quick word about the picture. So my dad is a fisherman. And every summer we go on fishing trips. And so last summer we went, I'm from a place called Vancouver Island. We go up on the North Island to go fishing, and there just so happened to be a guy there who liked math. This is not my boat, but that is a picture I took of a boat. Okay, so I have a lot of slides and not a lot of time, so I apologize in advance for going a little quickly, but it is what it is. It's already frozen.
It's fine.
I get it. Yeah, that's right. Yeah,
Everyone gets an extra minute.
yeah. The conference will end a little later.
We are so sorry about it.
Pardon? It says math boat. Yeah, I thought it was funny. So anyways, okay. So let's just give a quick rundown of what I'll be talking about. Obviously, I'll have to introduce this theory of weightings. And so that will be the definition and the corresponding morphisms. Associated to this weightings, you get this like sort of new normal bundle and a new deformation space. They're the total spaces of vector bundles, but they're not canonically vector bundles. And then, so these first 2 points were already done by Eckhard and Yanni. And then I wanted to understand a little bit more about, what are the sort of submanifolds in this category? What are the submersions? And once we understand that, we can talk about what a weighting for a Lie groupoid should be. And then after a little bit going into vector bundles, we can talk about the infinitesimal analog for Lie algebroids. And then also basically what one expects. We can get, starting with the groupoid, we get one for the algebroid. Okay, so the idea of a weighting is that one would like to modify the notion of order of vanishing. And so how one does this is they start off by fixing some weights. Here I demand that they're positive or rather non-negative integers. And then the weighting is defined by a filtration of the sheaf of smooth functions on your manifold, such that locally you have these coordinates so that the elements of the functions of weighted order I locally look like this. So the sort of weighted Taylor expansion starts in degree I, where here this sort of order of the multi-index is sort of this weighted order. I mentioned that I want these things to be sort of a generalized order of vanishing, or sorry, we also have weighted morphisms. It's the obvious definition, just you have a map between manifolds such that the pullback preserves the filtration of the sheaf of smooth functions. I mentioned that this should give you sort of a generalization of order of vanishing. In this generality, the first term is always the vanishing ideal of some sheaf of functions, or sorry, of some submanifold, embedded submanifold. And if n is given to you in advance, we refer to it as a weighted manifold pair. So in this sense, I think it's sort of as like an enrichment of the category of manifold pairs. So the first example is order of vanishing, right? So we just pick some submanifold. We say a function has order I if it vanishes to order I along that submanifold. But you can have more subtle examples, I suppose. So one example is if you look at just R squared in the origin, we could say that X has order 1 and Y has order 3. And so the filtration that one gets if they do this is, okay, this is your first order terms, X has weight 2, or this has weight 2, this has weight 3, weight 3, weight 3, weight 4, weight 4, weight 6, and so on. So you're getting in between terms here. Okay, so associated to this, or you get a filtration of vector fields. Namely, a vector field has order I. If when I pair it with a function of order j, I get a function of order I plus j. And likewise, we get a filtration of the k forms by how they act on k tuples of vector fields. Okay. And sort of the structures that one gets with the weighting are the weighted normal bundle. So mimicking how one can define the normal bundle in terms of this associated graded algebra, we look at the associated graded algebra to the weighting, and we get this space defined as its character spectrum. So this is the weighted normal bundle. It has the structure of a graded bundle in the sense that there's an action of R, but it's not a vector bundle action. So it turns out to be the total space of a vector bundle. And actually the total, it's the vector bundle that it is the total space of is isomorphic to the regular normal bundle, but not canonically, and the scalar multiplication is different. And also, yeah, the graded algebra lives inside of the smooth functions on this manifold as polynomial functions, and it's functorial for weighted morphisms. Again, mimicking this sort of construction by Hadge and Higson to define a deformation space, so a sort of like families of manifolds over R. One looks at the associated Riesz algebra and does the same thing. You look at the character spectrum. This thing turns out to be a manifold of dimension m plus 1 in such a way that the elements of the Riesz algebra live inside as functions on this manifold. Smooth function, and it's functorial for weighted morphisms. Okay, so I wanted to know, oh, well, let's look at some examples. So this deformation space comes with a surjective submersion onto R, and it breaks into a sort of, like I say, a family of manifolds over R, where away from 0, you're just getting M back, and over the fiber at 0, you're getting this new normal bundle defined by the weighting. So like one example is you look at the trivial weighting of the pair groupoid along its diagonal, its objects, you get Kahn's tangent groupoid back. Okay. More generally, you can also get this oscillating tangent groupoid that Venner, Bianchi, and Choi-Ponge have made. Okay. So in that example and in the one I mentioned, these things, you started with a groupoid and you output a groupoid. The normal bundle and the deformation space are both groupoids. And I want to know, just from the purposes of index theory, because Kahn has this beautiful proof of the index theorem using this tangent groupoid, I want to know, if I have a weighting of a groupoid along something, H, what are the correct assumptions I need to give in order to make this weighting multiplicative, or what should the right notion of multiplicative be? And the answer is obvious. You know, to define a groupoid, you have all of these things, and let's just put the adjective weighted in front of them. But the issue is, like, when we started this project, the term weighted submanifold wasn't understood. The term weighted submersion wasn't understood. And also, to define multiplication to be a weighted morphism, well, we need a weighting on this object, the space of composable arrows. And it's not clear a priori that this should be weighted. If you have a weighting of G, how do you weight this? Because it's not just the product, it's the fiber product. So there's something a little more there. So let's go on. A submanifold of a weighted pair is called a weighted submanifold if I can always find weighted coordinates which are simultaneously submanifold coordinates. Okay, so in some sense you get like a bifiltration on functions. If such a thing exists, then we get a weighting of the submanifold along the intersection given by this, and the embedding of R into M is a weighted morphism. So to sort of show that this is a non-trivial definition, the weighted submanifolds in the case of a trivial weighting are exactly the submanifolds which intersect the manifold along which we're weighted cleanly. But it's somehow more than that. If you have a non-trivial weighting along a point, then you can get manifolds which intersect the sort of critical submanifold cleanly, but they're not weighted submanifolds. So one example is this. If you look at the curve y equals x squared, it's not a weighted submanifold. Somehow when you do this, you're saying, well, y should have weight 2, but I've said it has weight 3, and this just doesn't work. Okay. So now that we know this, we want to know what are the right maps such that if I look at the inverse image of a weighted submanifold, I get a weighted submanifold. So, okay, this should be what a weighted submersion is. And the easiest definition is just to define it like this. Okay, it's somehow not a very satisfying definition in the sense that you're sort of defining your way out of a problem. But I didn't write them down, but I wanted to emphasize that throughout all of this, we have sort of like infinitesimal analogs of like what these conditions mean. And, you know, in the same way that one does in like a intro to differential geometry class, there's sort of like the tangent condition we need. But in any case, if one gives this definition, then one can always find, you know, weighted coordinates, which are also submersion coordinates for the function f. And so because of that, one has this property that one expects. If you had a weighted submersion from one manifold pair to another, and you took a weighted submanifold of the image, or the target rather, then its inverse image is a weighted submanifold of the domain. Okay, so why is this nice? Well, now I can give this definition. I know what this word means. I know what this word means. And one example that I didn't write down of a weighted submersion is the anchor map of pair groupoid. So if you take the pair groupoid, so we're assuming that S and T are both weighted submersions. So then the map from G into the pair groupoid will again be a weighted submersion, and the pullback of the diagonal will then be a weighted submanifold. Okay, so we can give this definition, and then one wants to know, oh, did it work? And the answer is yes. And this is more or less just functoriality of these constructions. So now that we know what all the words mean, we get this for free, basically. Right. So now I have groupoids, and I wanted some examples. So, right. So I mentioned I just had some submanifold H. I actually didn't, it's automatic from the multiplicative adjective that it has to be a subgroupoid, not necessarily wide. So you could have a subgroupoid along some proper submanifold of the object space. One example is, Kahn's tangent groupoid, where you look at the trivial weighting. A more fancy example is this oscillating tangent groupoid, that Van Erp and Youngkin did. So here, the difference, it looks the same, but we're getting different things here. The difference is the weighting, but I've sort of like buried that for the sake of time. Right, okay, so now I have all of these groupoids, and I want to know what's the infinitesimal analog. The first issue that one runs into is that a Lie algebroid structure is given in terms of its sheaf of sections, whereas a weighting is given in terms of the sheaf of smooth functions. So one would like to express the weighting condition in terms of sheaf of sections, and this is what one can do. So if you have a rank K vector bundle over a weighted manifold, so we're demanding that the base be weighted, then again, we just give the same definition, but we're allowing here for negative weights, and I'll explain why. So basically, we take a filtration of the sheaf of sections, and we just demand this local triviality condition. So instead of weighted coordinates, we have a weighted frame, and we want sigma to have sort of weight I if and only if we can write it in this way, where each of your coordinate functions have the sort of weight you expect them to have, I minus VA, so that the sum of the weights is I. Okay. So if M and N is a weighted manifold pair, then this filtration we got on vector fields is a linear weighting of the tangent bundle. And this sort of the other weighting we got, or the other filtration we got on one forms was a weighting of the dual bundle. More generally, this is an example of this phenomenon where if you have a linearly weighted vector bundle, then its dual bundle is canonically weighted in this way. And so once we have that, we can talk about like what weighted morphisms of vector bundles are. We could also talk about weighted comorphisms if you want, but it's all the same. Or maybe not the same, but it's as expected. So we then want to mimic all of the constructions that were done by Janus and Eckhard. So you look at the associated graded module. This is now a module over the associated graded algebra of smooth functions. You do the same thing. There's sort of this like weird phi in the denominator there. So let me just say, if I take this psi and I take one of these, an element of the graded module, and I multiply it by something in the associated graded algebra, then I want this to be phi of f times psi of sigma. remember these things are the homomorphisms from the associated graded algebra to R. Okay, and again, we just do the same thing for the deformation space, where we look at the associated Riesz module, and we do the same thing. I also want to point out, this definition looks kind of strange, but like if you just deleted the word Riesz and you looked at this sort of construction, and here you just put M, so there's no weighting, you get V back. Or I guess in this case, you would get V times R back, but in the previous case, you just get V back. Okay. Are there any questions? Yeah.
Is that the end of the talk?
No,
Oh,
I wanted to breathe. Okay. So, okay, now I have the correct definitions for vector bundles. I want to say, well, what's the condition I want for Lie algebroids? Or what are the right definitions? And this is the slide that gives me the Poisson merit. So we have a linearly weighted Lie algebroid. So it's a Lie algebroid, which is weighted as a vector bundle. Then we have a couple of equivalent conditions, as one probably would hope. So we need the bracket to be additive of filtration degree, and we need the anchor map to respect filtration degree. This turns out to be equivalent to I always called it the Durham differential, but I guess it's more properly called the Chevalier-Eilenberg differential on this complex. So again, A is weighted, so the dual bundle is weighted, and we have a sort of a bi-weighting on this, or we have a weighting up of this, and we want the differential to respect that. Okay, or we could ask for the Poisson bivector on A star to have filtration degree 0. So another thing that I sort of buried is we could define a weighting of a vector bundle in terms of its sheaf of functions. But instead of looking at all functions, we want to look at just polynomial functions. And we want to allow the base coordinates to have positive weights, but the vertical coordinates could have negative weight. Okay. And so if one does that, then the whole thing works. And actually, the definitions of the deformation space and the normal bundle are the same as the one that Eckhart gave. So that all works out as one would expect. Yeah, just the cost is that you can only allow the fiber coordinates to have negative weights. I don't know if I mentioned this explicitly, but it was demanded upon us that we allow positive and negative weights by the tangent and cotangent examples. So we have to, if we want a good theory, we have to allow this. And if any one of these three conditions holds, then we say that it's infinitesimally multiplicatively weighted, and we can define the weighted morphisms in terms of the VB morphisms, which are chain maps for the complex. Okay, good, 3 minutes. I've been burning through this, which is good. The theorem is, okay, yeah, we get Lie algebroids. The normal bundle and the deformation space are Lie algebroids. And the thing that one might hope for is the Lie functor commutes with this weighted normal construction. So this is my last slide. I have 3 minutes. I'm going to give an example that I worked out yesterday because I was like, yeah, this should be true, but I never actually figured it out. Okay, so if one looks at the tangent bundle, you could say that the sections of the tangent bundle of weight -1 are just all vector fields, and the sections of the tangent bundle of weight 0 is just 0. This gives you a weighting of the tangent bundle. The weighting of the base is just trivial. We say C infinity M0 is everything, and C infinity M1 is just 0. So every function has weight 0 and no functions have weight 1. And what one gets if they do this is the weighted deformation space is just Tm over M cross R. And the bracket on this is just T times the bracket on Tm, which is what one expects. So the bracket at a point T is the T times the bracket, where this is the bracket on the regular Lie bracket. So in particular, it degenerates to the zero bracket over the zero fiber, which tells you that this is actually the Lie algebroid of Kahn's tangent groupoid. So that's what I'll end with. And more generally, actually, we get the Lie algebroid of this like oscillating tangent groupoid and so on. So that's all I have to say.
Thank you so much, Daniel. Are there any questions? I see two hands. Yes.
Thank you for inspiring talk. So I just want to clarify. So you have coordinates to which you assign weights.
Yeah.
And then for change of coordinates, do you require that the total weight is preserved entirely or only less or equal when you change coordinates?
Yeah. So I guess you want your local coordinate transformations to be weighting preserving. So I guess, yeah, in principle, it could lower the weight.
Oh, you can. So that's the difference. So you have filtered manifolds in comparison to graded manifolds.
Yeah. Yeah. Yeah, I actually don't understand the connection to graded manifolds, but I would like to understand it.
Well, for graded manifolds, you have weights exactly as in your picture, but then the change of coordinates, transformation coordinates are just preserving just the total weight.
Yeah.
And but of course, one can consider straight filtration. So
well, the thing is that like the weight of a function isn't super well defined, right? Like because it could if for instance, like it's order of vanishing. So like if a function vanishes to order 2, then it also vanishes to order 1. So there's sort of, I guess there's like a minimum weight or a maximum weight it could have or something. So in that case, yeah. I'd have
yes,
to
I'm just asking that. Well, if you have grading, then of course you can consider what you said. You can consider a straight filtration.
Yeah.
So, but if you have just I simply wonder if in your category the changes are not supposed to preserve grading exactly, right? Only up less or equal, only preserve filtration, right?
Yeah, they just have to preserve the filtration, I think.
Because at some point you said you have a straight graded bundle, and which is I think just graded manifold in a in proper sense, right?
So I'm thinking of a graded bundle in the sense of Grabowski and Rodkiewicz. So like
Well,
Maybe we could
talk.
during the break. We would have
Like when I say a graded bundle, I literally mean a manifold with an action of R, a monoid action of R. That's
yeah,
it.
well,
That's the definition.
What's called graded manifold. It's well before Grabowski and Rodkiewicz. Anyway, we can.
This is my understanding of it. Yeah.
Thank you. We have one more question. Maybe just a brief discussion, and then we can continue the conversation during the break.
Of course.
So I mentioned actually in my talk Enriquez's paper on higher Lie groupoids, and there you need not just a notion of submersion, but surjective submersion.
Mm-hmm.
And I'm wondering so I think that this is ready to go, and you probably would get a theorem that delta takes weighted Lie n groupoids, let's say, even in the Banach setting, to weighted to Lie n groupoids. But we need to the one thing we need is a notion of surjectivity. And I'm just curious if you think the notion of surjectivity would just be surjectivity of the underlying manifolds, or if there could be a greater subtlety.
Yeah, no, I kind of feel like it would just be regular surjectivity. So like the definition, like the way that I thought about basically like the original way that I thought of a weighted submersion is so one way you can define a weighted submersion is in terms of these local sections. And so that's what I wanted to do, but somehow I think surjectivity is probably the same. I will say that I don't know how one would define a weighting in the Banach setting, because we have this local triviality thing, and I don't know what one would do if you had lots more coordinates.
Yeah, the weighting would only be a finite number.
Yeah. Sure. Yeah. No, thanks. That sounds like an interesting perspective.
Thank you, Daniel, again.
Yeah.